Okay, let's round out your course in Precalculus with a little bit of calculus. Yes, you're ready for it now. And Precalculus is a lot of the heavy lifting for calculus, and when you start calculus, you will be reviewing Precalculus again. So it's all bits of analysis that will help you, even if you don't go on into calculus proper. But we'll get a little bit of calculus today when we talk about limits, and we talk about limits of average rate of change. First, I want to work sort of a simple problem in limits. Let's say we want to know the limit as x goes to minus 3 of x squared plus 5x plus 6 over x plus 3. Alright, so you can look at this and you can see, well, the bottom goes to 0. And one of the properties of natural logs is they have a lot of properties. Property of the limit, sorry, not natural logs. One of the properties of limits is limit of say f of x plus g of x. The limit of those two things together is the limit of f of x plus the limit of g of x. So the other one is the limit as x goes to a of, let's see, f of x over g of x equals f of the limit as x goes to a of f of x over the limit as x goes to a of g of x. It shows you these things break apart as you would expect. So you can find the limit in the top and the bottom. But notice this is only the case if the bottom does not go to 0. Bottom not equal to 0. Here the bottom is equal to 0 and the top is equal to 0. So we can simplify this and we'll get the limit that way. For really simple equations like x plus 3, what's the limit as that goes to minus 3? You can just put the number in, and whatever you get is the limit, unless it's some kind of piecewise function. We can factor this top, but we set it up to be pretty easy. I think this factors into x plus 2, x plus 3. Indeed it does. Just all over x plus 3. Alright, we know we can simplify this equation as long as we have the caveat that the bottom x cannot be equal to minus 3. But we're looking at the limit as it goes to x is minus 3. So this is going to be a function. It's going to look like x plus 2. Something like that. As this goes to minus 3. And that will have a hole at minus 3. Let's see. It'll be right here. Oh, no. It's going to be, let's see. It's going to be over here. It's going to be on minus 1. So here is minus 3. And this equals minus 1. But it has a hole there. Because, as we said, x cannot be equal to minus 3. But the limit, so we simplify this to find the limit of this. Once you get 0 over 0, you know you have to do some extra work and figure out if that simplifies or if there's other things we can do. And indeed it does simplify, and this ends up being just evaluated at minus 3 plus 2 equals minus 1. So the limit as x goes to minus 3 is minus 1. Alright, pretty straightforward. You should be able to do problems like that. But let's make it interesting. Sometimes these limits are pretty interesting functions. And often, remember we did the average rate of change? I'm going to draw your old friend e to the x. This is e to the x as a function. I said it was very interesting because the slope of this line is equal to the value here. So if we look at the average rate of change, which is this, the slope, if we could get the instantaneous rate of change, then that would be equal to the value at e to the x. Alright, and that's what calculus is all about, finding slopes of lines. And one of the ways it does that is to take a value, say x, and add a value x plus h, go a little farther down. And then you get f of x down here, and this is f of x plus h. And you find the rate of change, which is the change in y over the change in x. So your book uses that cool looking abbreviation, AROC. Average rate of change is going to be f of x plus h minus f of x, that length there, over x plus h minus x. Remember we did this thing way back a while ago, this average rate of change? Well, now we can combine the limits, and one of the reasons we're doing limits, so we can combine that. You can see that this slope is a rough estimate of this slope, but as this gets smaller and smaller and smaller, it gets to be a better and better estimate. But as this size goes to 0, this function ends up going to f of x minus f of x over x minus x. So it ends up being 0 over 0. So we have to do something funny to get the limit of these. So we're interested in the limit as h goes to 0. This is sort of the heart of calculus. Of this thing, I'm going to write it again. It's so important. You should see it again. Over, and this simplifies, you often just see the h down there because the two x's cancel out. Notice f of x plus h is not f of x plus h. You can't cancel that out and just have h up there. This is often a more complicated function. Let's show that for f of x equals e to the x. Let's see what happens to this limit. Alright, so let's put in e to the x for f of x. So we talk about the limit as h goes to 0 of e to the x plus h minus e to the x over h. Well, remember our properties of logarithms. E to the x plus h is e to the x times e to the h minus e to the x over h. Alright, these both have an e to the x in it. Let's factor that out. This ends up being e to the x times e to the h minus 1 over h. Right, so we factor the e to the x out. Now, as h goes to 0, the limit, as h goes to 0, with the limit we often just try and evaluate it at 0, see what happens. But here you see you get e to the 0 is 1. So this is 1 minus 1, which is 0. And it's 0 in the bottom here. So we have 0 over 0. We're going to have to do something to that. It doesn't equal 0. Turns out, it's very interesting, it equals 1. You can do that a couple ways. You can try values of h. I would try h equals 0.1, h equals 0.1, and try smaller and smaller values of h, and you'll see that you will get a value that's closer and closer to 1. We can do that graphically using your graphing calculator, or we can jump over to desmos.com, and here I typed it in. Instead of using x, I used h. And here's that function. It looks a lot like e to the x. And if you come along here, as it gets closer and closer to 1, this value gets closer and closer to 1. And notice as it gets to 1, it's undefined. So indeed there is a hole right there where our value should be. And as you come from the other direction, it's also getting very close to 1, but from the other direction. So you can look at it graphically and see that that does equal 1. There's another way I wanted to show you, which is using a series expansion. And these you will get to know because they're very handy later on. E to the x can be written as an infinite series. Alright, and expands, it equals 1 plus x plus 1/2 x squared plus 1/6 x cubed. Maybe you can see the pattern here. Plus 1/24 x to the 4th. So this is 4 times 3 times 2. This is 2 times 3. This is 2. Sort of this is the factorial, but we won't worry about that. But so as x goes to 0, we can evaluate e to the x using this expansion. This goes on to infinity. But these other terms make a smaller and smaller contribution as x gets larger. Alright, these all go to 0. And we can evaluate this expansion. That goes to e to the 1. So let's put this in here for e to the h. So we get this, write our limit stuff again, blah blah blah. E to the x times, let's put in 1 plus x plus 1/2 x squared minus 1 over h. Alright, this simplifies. These two ones cancel out. Oh, this is pretty neat. And, oh, sorry, these should all be h's. Because we're doing e to the h. That's h squared. So we end up with h over h plus h squared. H is going to 0. So this term sort of disappears. It's not very important. As it gets closer and closer to 0, this goes extremely quickly to 0. But we are left with h over h, which is 1. So the limit as h goes to 0 of e to the x equals, as h goes to 0, h over h. That simplifies. These cancel out. And they are the same thing. So that simplifies to 1, sort of the same way the previous problem did. And we end up with the limit equals e to the x. And the limit of this, average rate of change as that goes to 0, that's also known as a derivative. So d dx of e to the x ends up being e to the x. So the slope of the line here at e to the x is whatever that value is. So the slope of the line at 0 is e to the 0. The slope there is 1. That's pretty amazing. That's why we choose this e function, this number e for this. Because it has this property where you take the derivative of it, it remains the same thing. Extremely important for all analysis. And that's sort of one of the crown jewels of calculus. So there you have it. These limits lead right into calculus. And that's about it. If you have a solid understanding of that, you are well on your way and you have a nice foundation for your future in analysis.